So what you're saying is that this image hits layer one and a bunch of stuff happens. And if all things are good, there's an activation. The neuron fires or the neurons fire. I think is a better
Right.
way to think about it because I think in your example, every single weight or parameter is a neuron, right?
Right.
Welcome to Practical AI, everybody. This is season 2. My name's Jeff. I'm with Peter Lynn. Practical AI is sponsored by Pocket AI. Pocket AI is a tool used to perform surgery on your models to make them better. While everyone today is doing RAG and refinement, Pocket AI allows you to edit the weights of your model directly. Peter, we have used the term activation or activation layer quite a bit. I don't know that I've ever spent time with you just working on an active definition and describing it. And I'm so dumb on activations that we spent a long time prior to this call with you kind of explaining it to me. And I think before you get into your version of it, um, I love the picture of the Willy Wonka scene from that 1971 or 72 movie where Mike TV gets broken down into a million pieces
Right.
and gets reassembled as a smaller version in a TV set. And so I think that's a good image as we're kind of going through this. But why don't you explain to us, in your words, how activations work and what are they?
Yeah. So basically, if we think about human neurons, we have the cell body. On the cell body, there's all these like dendrites that are connected to other neurons, and then there's an axon, which then extends out in some direction and it connects to other neurons. And in a human or in creatures, we get stimuli that the cell gets, and after it hits a certain point, a certain threshold, it'll send a signal down the axon and then it'll try to stimulate the next neurons, one or more, down the line. And artificial neural networks, the activation part is this: when it passes a threshold, it's going to send a signal. So that's basically what it is.
Okay, so in computer vision, you have an image that's an input. It's coming in, it's going through layer one, going through layer two, going through layer three. Once it gets out the back end of the whatever the last layer is, that's an epoch. And so what you're saying is that this image hits layer one and a bunch of stuff happens. And if all things are good, there's an activation. The neuron fires or the neurons fire. I think is a better
Right.
way to think about it because I think in your example, every single weight or parameter is a neuron, right?
Right. So basically, in an artificial neural network, there's layers. So there's the input layer, which is what takes the stuff coming in. There's the output layer, which is the prediction. And then everything in between is called the hidden layer because it's opaque and you can't really see it. So image comes in of a dog, and you tell that, okay, this image is 30 by 30 or 100 by 100 or whatever it is. And then if you're using convolutional layers, it takes a 3 by 3 or a 5 by 5 and it moves it across your photo to scan it. And then so each one of those filters then takes that, multiplies against the weight. So basically it's kind of like when you do Photoshop, you can do a filter. You can turn the contrast up, or you could turn the brightness up, or you could like make it more red or more green. So it's the same thing, right? Image comes in, we got these weights, and they act just like those filters in Photoshop. It does a thing. And so what you get out of it is, some modified version of that picture. So for example, if I take a picture of a blue dog and then I tweak the RGB value, the red, blue, green values, I can make it look completely different color. Or I could jack up the contrast or the
Yeah.
brightness, right? And so that's what all these layers are doing. So the first layer does that. It kind of takes the weights, it applies it, so you get this filtering effect. And then when you get out of it, it's like some modified version. And so then layer two tries to figure out, by multiplying the weights against this a whole bunch of new inputs now. So you don't have one image, you have like 100 variations if there's 100 filters. Then it goes, oh,
Okay.
I got 100 variations. So now let me look for squares, or let me look for lines, or let me look for curves, or let me look for red. So maybe one filter is like, there's a lot of red. Another filter might be, there's a lot of blue. Then there'll be, there's a lot of like bright things, or there's a lot of dark things. So layer two then does whatever it needs to do, and it spits out another set of images. That's a modification of that other set. So this just happens and happens and happens. Towards the end of the model, it then figures out like, oh, these kinds of things that have gone through the model means it's a dog.
Okay, so a couple things in there. One thing that I didn't totally understand until today is that each weight is breaking that image down into multiple bits, essentially, multiple parts, right? So if it's, each bit on the thing, or if it's rows and columns or whatever,
Pixel, yeah.
it's every pixel, yeah, it's doing its thing against all of it,
Yeah.
right?
Yes.
Which means that once the image gets through the first layer,
Hmm.
each weight has kicked out some number multiplied times the image, right? I mean, because it's kicked, like, let's say an image was 1,000 pixels.
Yep.
That weight is kicked out 1,000
Yeah.
units, right? Or equations, right? And then what you're saying then is it does math,
Right.
multiplication and addition,
Yep.
and makes a determination whether it's going to activate or not. Is it either on or off, or is it fire poorly or positively or negatively? Like, how does that activation look? Is it like a neuron where it's either firing or it's not?
So the base operation is take the input, multiply against the weight, which gives you like a modified version of the image, and then you add it all up, and then you can pick different functions. These are called activation functions. So there's rectify linear units, there's sigmoid, so there's a couple different ones. So you take that data and you run it through the function. If it's above zero, it means okay, it was positively stimulated. If it was below zero, then it says, okay, well, we're going to suppress this because it's not useful. And so if you want, you could take the raw value, but usually that doesn't work very well. So usually you want to use either ReLU, which is rectified linear units, or sigmoid or something, or softmax, to like kind of like average it out and try to filter out the noise before you go, okay, send it to the next layer.
So in some way, you're kind of determining how you're going to weight
Yeah.
these
Yep.
out or the outputs. And I
Yeah.
think when you and I were talking about this, it seems like the first layer's role is pretty important, because if it's not going to do a good job up front, it's going to be hard for the downstream layers to make any sense of what's happened, right?
Exactly. Yeah. So for example, let's say you're a computer science student and your professor says, hey, write me a new framework for neural networks. And you go, okay, great. And you're like, wow, this is fun. And so you initialize your weights initially, but you do it poorly. And they're all like, instead of being a nice distribution between -1 and 1, they're all like, they're all between -0.8 and -0.9. Right? So in that case, your model will never get anywhere.
Got it.
Because basically
So
it's going to suppress everything.
yeah, if you could get the first layer better, it's going to be better long term. And so I'm assuming that there's some research around that in ways that they can make the first layer in the framework better, right?
Yeah, so a few years back, there's several papers about that there might be like a core set of kernels that people have figured out work well. So meaning that like, okay, we've taken the public data sets like Coco, ImageNet, CFAR, whatever, and we've trained a model and we figured out roughly a good set of weights that ends up extracting or ends up noticing the right features that we want. And so in theory, you could take those as a base instead of just saying, I'm just going to randomly initialize the weights. You can take those as a starting point.
Got it. Okay, so if we switch over to LLMs, it kind of makes sense that each weight in the first layer and successive layers would look at, break something down into pixels or something. What is the multiplication that's happening for LLMs?
So LLM, it's a little different. So transformers have a weight, but they also have the attention. And the attention has the key, the value, the query. So it has so the reason why transformers work so well is that this attention mechanism is like a short-term memory thing. And so as you feed it data, it remembers the tokens that it's seen and it weights those so that next time you get some more data in, it goes, oh, these tokens were more useful. These other tokens were not very useful. And so then it's going to try to improve or change the weight so that it gets better for the tokens it thinks are more important.
Got it. But it's still, each layer is still doing activations.
Yes, at the end of the day, it's just input multiplies against the weights.
Yeah.
Because really the attention part is most useful during training. When you're just asking GPT for things, it's just the weights at that point. It's mostly just the weights.
Okay. And then finally, with each successive layer, when you're multiplying times the next amount of weights, the values are just getting almost exponentially larger with each layer, correct?
So it depends on how you configure the layers, but in general, the input comes in, and then there's this explosion. So this is a term called high dimensional data is a commonly used term in machine learning because in order for the models to learn, it has to take the input and then it explodes it out. And then so from that, it's able to figure out like, oh, these are the important things in the data that I'm seeing.
Got it. So what's the future sort of improvement in this space, do you think? Where's the research and the innovation going to happen in activations?
So right now, the kind of the primary focus for activations is trying to map activations to try to understand what the activations mean, which it's an ongoing topic and there's still a lot of work that needs to be done. So that's the current focus in the industry. Um, there's some suggestions that progress is being made by Anthropic and other people, but it's still in the early stages.
Wonderful. Well, this is a good topic, Peter. Thanks for giving us a deep dive in it. This is a little bit more technical than some of our other ones, but it was super helpful for me. Hopefully everyone learned something. If you have questions about this, please leave them in the chat and we'll try to address them. And until next time, when we come up with more topics, thanks everybody. Take care.